We're going to start this out really basic and just talk about some of the fundamentals of culvert durability. And then later on, the guys in the session are going to talk about once the durability doesn't work and then the longevity of the pipe isn't there, how we fix it. But what we'll talk about is just some of the general topics. Before I really get into it, one thing that's really, really important to understand is that when you're talking about pipe durability, particularly culvert durability, there can be a lot of variation. So all the numbers I give you, I'm giving them like they're hard numbers, but you have to understand that these are not hard, fast numbers. These are very, very broad ranges of numbers that are acceptable, but it would have been way too hard to get up here and say between this number and give all kinds of ranges. So I just threw numbers at it, and the numbers they're decent, but there is significant variation in the numbers. Okay, so get started. So today, this is what we'll talk about. We'll talk about some durability concepts, how metal, concrete, and plastic culverts react to different environmental conditions, what are the things we have to be worried about, things like that, and then we'll kind of wrap things up. So what is culvert durability essentially? Durability is essentially it's a resistance to the environmental degradation, and that degradation takes a lot of different forms. It can take corrosion, abrasion, and when we talk about thermoplastics, the thermoplastics is more of a material degradation of the polymers inside of the plastics. And so we have that a little bit different. We're not really calling it corrosion or abrasion. I just set it aside and I say it's thermoplastic degradation. There's a lot of other stuff that goes wrong with pipes when you're in the field. And things like your joints, things like the structural overstressing pipes, freeze thaw if you're up further north. Freeze thaw is more of an issue if you're very cold and you have shallow cover, because typically if you're in deeper cover, there's a heat sink from the surrounding soil. You never get into a situation where you're going through freeze thaw. So this is more of a northern shallow cover phenomena. And then finally, installation. And then we won't talk about all the things that contractors find to do wrong with sticks of pipe, which I could talk for days and days about. But we'll stick to just some of the more general ideas of culvert durability. When we talk about corrosion, we're basically talking about acids. It's the easiest way to say it. If we're less than 5.5, it's a really strong acid. If it's greater than 8.5, it's a strong alkaline. I think with the exception of maybe Utah, that kind of an area, there isn't really high alkalinity anywhere else in the country that I'm aware of. I think that's the one place that you see really, really high alkaline. But that's my recollection off the top of my head. But that's the only place you really get the only other place you may see it is when certain fertilizers are used and you're getting runoff from farm fields and you have really, really high usage of different types of fertilizers, you can actually get very alkaline in that particular case too. Okay. Resistivity, which is a measure of the ability to conduct an electrical current. It's the inverse of conductivity. So if you have a really low resistivity, that means that its transfer of electrons is very easy for the material. And the flow of electrons speeds up corrosion. So when we're talking about resistivity, high resistivities tend to be better than low resistivities. And then the other thing about resistivity is resistivity can either be in the soil or it can be in the water. And so you have to be concerned with both soil and water resistivity. Other types of corrosion would be chlorides. And basically what happens is your chlorides will decrease your resistivity, as I just talked about. If we decrease the resistivity, we have more electron flows, we have greater acceleration of corrosion. So that's kind of how chlorides work. Sulfates, high sulfates lower your pH. The other thing that sulfates can do is sulfates deteriorate the concrete. And basically what they do is the concrete almost starts to become powdery. And so any type of abrasion can then get rid of your concrete cover, exposure reinforcing in your concrete pipe. So sulfates tend to be pretty damaging to reinforced concrete pipe. Microbial corrosion. These are lots of different things, lots of different ways that we get microbial corrosion. But most of the time, you have to have standing water and high humidity. If you have sort of high humidity, standing water, things like that, that's when microbial actions start taking place. That's when you can start seeing microbial degradation. Okay. Abrasion, which is just progressive section loss from abrading away of the surface of the material. It's almost always you see it in the invert. You typically wouldn't see it anywhere else. High bed load, high velocity. The interesting thing is that there's a misconception, I think, that people think that you have to have high events to trigger corrosion, and that's not the case. Actually, or abrasion rather, what's actually more detrimental when you're talking about abrasion is when you're talking about low flows that have the ability to move bed load. Because if you have low flows that are moving bed load, then you have a repetitive process that's going on multiple times. And that can be much, much more damaging than any high event will ever be. So when we're talking about abrasion, we're usually talking about normal flow and the ability of a normal flow to move a bed load. And again, how big is the bed load that it can move. Glenn DeCoux at Caltrans, him and one of his colleagues, they went and they put out what was by far the most comprehensive assessment of culvert abrasion. It's really, really well done. I'm not sure you can read that very well, but it's not important to have the exact numerics because you can go to Caltrans and you can get the document if you want. But basically what it's saying that level 1 is no bed load with very low velocity, and 6, which is the very highest, is very, very heavy bed load, sands, gravels, rocks, rocks up to 6 inches that move fairly easy. And in order to get that type of a rock to move fairly easy, you need really, really high velocities, over 12 feet per second. And again, we're not talking about extreme events or design events being able to move this type of velocity. We're talking about, normal events that happen on a, yearly basis. That's what's much more damaging. So when we're talking about these durability concepts, that's what we're talking about, okay? The other interesting thing is that when we talk about corrosion and abrasion, you always have to think about them as a combined process, because if you look at abrasion by itself and you look at corrosion by itself, and if you add those two together in terms of the longevity of the structure, those two acting in concert is much, much greater than those two acting independent of each other. It's actually it's exponentially greater. And so you can see extreme degradation of pipes when you have high abrasion and high corrosion. Well, I think that's enough. Well, nah, I'm gonna leave that alone for now. So I had something else I want to say, but I'll hold my tongue on that. So thermoplastic degradation. And so what we're talking about when we're talking about thermoplastic degradation, the main forms of degradation will be oxidation. And so basically over the longevity of the pipe, oxidation, oxygen packages inside of the polyethylene can degrade, oxidize essentially. And as you oxidize, you end up with brittleness and cracking in the pipe. The other thing you can get is what's called slow crack growth. So slow crack growth is a phenomena when a pipe under relatively low constant stress, so the pipe will be nowhere near the strain limit of the conduit. So you're nowhere near the upper strain limit, and if you have a sustained long-term stress that's below the strain limit, you can still get cracking. And normally it occurs when there's some sort of an imperfection in the wall of the polyethylene, so inside of the material itself. If you have a little bit of dust or something like that inside of the polyethylene, that's a point of discontinuity, and that can create slow crack growth. So finally, the last thing is UV degradation. And so basically polyethylene is susceptible to ultraviolet light from the sun. So if you took just virgin polyethylene and if you kept it in the sun, in a matter of months, it would become extremely brittle and would start to degrade. So what the manufacturers do is they add carbon black to the mixture, and the carbon actually coats the molecules of the polyethylene, and it protects it from UV degradation. So, all right. So now let's get into some of the actual pipes. We'll talk about how we can kind of help these things. But for steel, we have lots of different coatings. Galvanized is your base galvanizing. You can also get aluminizing. You can get bituminous coating, but I think bituminous coating is kind of slowly disappearing because of the environmental concerns of a dip tank. So the dip tank is not the cleanest environmental process you're ever going to see. I think I'm being kind when I say it that way. But I personally think that it's not going to be long before bituminous is no longer available, except for in very, very small markets. It's just the environmental impacts of bituminous plants are too much, and as equipment comes out of service, it's almost impossible to get a new permit to install a new dip tank. So there'll be a day, and I don't think it's that long away, when bituminous coatings, you can't get them anymore. Polymer coating, which is basically a sheet of a polyethylene polymer that you coat the pipe in. You melt it, basically you melt it to the wall of the pipe. There's enough holidays inside of the pipe that you actually create a mechanical bond between the polyethylene sheeting and the corrugated metal. Very durable, very, very durable coating. And last thing is invert paving. I think some of you probably know about invert paving, but invert paving is I think it's more novel. But basically what you do is you just pave the invert of the pipe with concrete. So you put some mesh down, tack the mesh onto the invert, and then for about 1/3 of the circumference of the pipe, the lower 1/3 of the circumference, you pave it with concrete. That concrete becomes your sacrificial layer. You never really affect your base metal. And so then now you have a much longer lasting conduit. Okay. Aluminum, there aren't any coatings. Aluminum is aluminum, but it does pretty well. Some ranges. Steel pH between 5.5 and 8.5 is usually okay. Now keep in mind that there might be coatings that you need, and this also depends on, as I talked about earlier, when you're talking about this, you have to understand the importance of the abrasion corrosion process working in tandem. So basically what the process is we create a scale on the pipe from the general pH of the water. If the pH is low enough, we start creating a scale on the pipe. That scale, if it isn't abraded away, actually acts almost like a weathering steel, and that scale protects the base metal. However, if we abrade that scale away, we now are back to bare metal, which corrodes, and we repeat that process over and over. And if you have a highly abrasive site, you repeat that process very, very quickly. As an example, if you're in one of those higher ranges of abrasion levels, a metal pipe, even like say if you were to use like a bituminous coated, you really need to be pretty close to neutral in your pH if you're at a very abrasive site, and it kind of works its way back from there. So if you have less abrasion, you can come down lower in your pH, but so it's kind of a balancing act. And when you're talking about how metal pipe works, resistivity is above about 2,000 to 5,000 ohm centimeters. And steel on its own without some sort of paving, really, really high abrasive sites, you should avoid it. You should just avoid the pipe when it's really abrasive, because without a coating, that abrasion corrosion process is just, you can, I've seen pipes 3, 4, 5 years old that the inverts are completely rusted out and gone. The inverts are gone just because of that corrosion process. Aluminum, as long as aluminum is between about 5.5, 8.5, resistivity is above 1,500, it'll last a pretty good long time. It'll give you your design service life. It should give you 75 years without too much difficulty. Really, really high alkaline isn't very good for the aluminum. So when you get really, really high in alkalinity, aluminum doesn't do so well. So as an example, you probably don't want to concrete encase aluminum pipe, because the alkalinity of the concrete can actually damage the wall of the aluminum pipe. And I say here, not recommended for highly abrasive sites. The only reason I say that is because there's never been any testing done on it that I know of. Now, if there's work out there that I'm just not aware of, maybe you can get higher in your abrasive range, but just from what I know, very, very abrasive in aluminum has never been tested. Okay. Concrete, move on to concrete culverts, we'll talk about. Concrete's generally anything above 5 is no problem at all for concrete pipe, and will give you extremely, extremely long service lives. Under 5, there's different things you can do. You can use special concrete mixes with high alkalinity, which will help to offset the acidity in the water. You can use sacrificial concrete cover, and there are coatings, but I'm aging myself because we used to epoxy coat them, and we used to put in vitrified clay plates in the invert of concrete pipe, but I've been told that by my concrete friends that those things are kind of a thing of the past. So now I think the big things that are being looked at are admixtures, things that you can put in the concrete to make them more resistant, and using additional concrete cover over your reinforcing to act as a sacrificial layer. Then with your sulfates, we talked about earlier, the sulfates and how the sulfates can degrade the pipe. So generally the way that we can combat that is by using special types of cement, like a type 5 cement is actually pretty good in terms of resisting sulfates. Another thing that you can do is coating, and this is one that me and one of my concrete friends were just talking about a little bit ago, was you can actually add like liners to the concrete pipe. If it's bigger, usually more effective for bigger pipe, but if you have larger diameter pipe, you can put in a PVC coating, and it's a mechanical connection. Again, it's mechanically connected to the wall of the concrete, and so you do that. You have a really nice, long-lasting sacrificial layer, and you'll get tremendous wear out of your reinforced concrete pipe, even more than it already has, which is already really, really good. So, yeah. But it makes it really attractive in like sanitary markets. So if you actually have like a sanitary flow or something like that, I've seen PVC coated reinforced concrete pipe used in that type of an application pretty frequently. Okay. One thing to be cautious of, even though if you have not so low of pH and the things that are kind of damaging the concrete, you have to be worried when you have high chlorides and you have cracks greater than about 2/100 of an inch. So at this particular point, this is when the reinforcing in general, again, everything I'm talking about is general. I don't want to say this is the hard, fast number because it's not that simple. This is really, really, these are complex processes that are very difficult to repeat when you go from one state to another state to another state. Particularly now, I'm talking about concrete now, but particularly with metal. With metal, state to state to state, the results vary a lot. Now, concrete and aluminum, if you go anywhere in the country, you'll get pretty close to the same range of acceptable values. But metal has a really, really high variability. As an example, most states in the country who have done durability studies, resistivity was a factor. It was a significant factor. In the Ohio study, which was done the first one was done in 1972, the last one was just completed about 2 years ago, resistivity was found not to be a factor. So that type of variability it exists. It's natural variability, and it's different environmental conditions that you run across in different states. Okay. Excuse me. So anyways, chloride's greater than about 500 parts per million, and cracks greater than about 0.02 inches. So greater than about 2/100 of an inch. With chlorides greater than 500, you can get a situation where you're actually starting to break down the reinforcing steel inside of the concrete pipe. Okay. Plastics. Generally, they're inert to corrosion. There's very little in the natural environment that will degrade polyethylene. Its resistance to abrasion is actually quite high, but it's not well documented. So just as an example, there are installations in South America where they're using this to bring water for mining operations, and they're using a half-round piece of polyethylene, and the water is going 30, 40 feet per second, and it's carrying bed load, and the pipes are working perfectly fine. So, but it's not documented. That's just, I know that from my contacts. So I think it has really, really high resistivity to abrasion, but it's not well documented. So keep whatever that's worth. Oxidation and slow crack growth, both of those are handled through the material standards. Basically what they do is they have material standards in place that make sure that there's enough antioxidant packaging inside of the polyethylene and that there is enough resistance to slow crack growth. And so they do that through different types of testing to make sure that the polymer blend that you get, and so basically what they do it through what's called a cell class. And if I'm boring you with like too much detail, I apologize, but I love this stuff. So. It's hard not to get excited about things that you actually like. So, anyways, it's amazing because 30 years ago, this was thought to be a very difficult thing to do, to be able to actually get it to where you could have a pipe that would be really resistant to slow crack growth. And it was thought that it would almost put the manufacturers out of business because of the cost of the polymer. The actual pellets of HDPE will become so cost prohibitive that they couldn't bear it in the marketplace. It's a great thing about the marketplace. The marketplace has now responded, and this is fairly straightforward for them to make. And so now basically we take care of those two things pretty simply through the mix of the polyethylene. Degradation, polymer additives, what I talked about, there's different types, but carbon black is by far the most widely used. Titanium dioxide is another. There's different types of polymers that they add to the polyethylene to stabilize it and keep it from degradation of UV. Having said that, I still don't think it's a good idea to have pipe exposed to the sun long term. Even though they have the stabilizers, I've seen too many situations where even in that situation it can be brittle. So my recommendation is if you have a polyethylene pipe, put a head wall on it and bury it at your outlet. Just don't keep it exposed. That's, I don't have any, I have no documentation for that anywhere. I have no source for that other than my experience looking at pipe for close to 30 years. Okay. Last thing I'll talk about is fire. Most pipe types will experience some damage under intense fire. There's just no way around it. But when we're talking about the risk of it, it's very, very low. And so I'm not always sure that you need to protect from fire unless you're in a case where you have forest fire or brush fire that are in the area. If you have those types of situations, I personally would say don't use bituminous coated steel pipe or HDPE because those two things under a sustained fuel source can burn. All right. That's it. So I thank you for your time. Do I have time for questions or no?
Yes, we do have time for questions. Microphone, so if you're going to have a question, raise your hand and I'll bring it to you.
Have you had experience with metallurgic reactions between, let's say, steel bolted connections? So you have an aluminum plate culvert. They typically use some steel, 3/4-inch bolts.
Yep.
Have you seen any adverse impacts with that connection there?
No, I've not. Now, I would suspect that if you have the right soil conditions, you probably could.
Okay.
But in general, I don't. I would think that the aluminum would generally be fairly inert from that. But I could see that the bolts could still rust, for sure.
Bolts. Okay. Thank you.
All right, any other questions?
Depends on who you ask. Anywhere if you're asking me personally, I would say somewhere in the range of 30 to 50 years. If you're looking at documentation will tell you anything from 20 years to 100 years. But me personally, if you say give me a hard fast number, I'd say 50 years. But that's based on just my gut and looking at pipe, nothing else. Yes. That is one area where I am not terribly well documented, to be quite honest with you. Because really, when it comes down to it, the only one who really works in that area is Florida. And so, my suggestion would be if you want to understand how to go about that particular, I would look at Florida. Because Florida has done a lot of work on coastal environments and how to look at pipe durability in coastal environments. That would be my suggestion. And since there's not a lot of seawater around here. I'm from here, so not a lot of seawater around here, so it's not my strong point, to be quite honest.
All right, that's all the time we have. Let's go ahead and give Kevin a round.
Thanks.